We've already talked about basic circuits with only one resistor and one power source in there, but most circuits don't operate in that simplistic manner. In fact, most circuits have a more complicated idea with multiple resistors spaced periodically, sometimes even more than one. Here, only one power source. And they're in series and parallel, all sorts of combinations. But to get to that, we have talked about simple series and parallel circuits and equivalent resistance. Now, equivalent resistance is the total resistance of all the items in the circuit, or the total resistance of the circuit. So in other words, it's like trying to reduce this complex circuit over here into a simple one with one resistor. How does all of these resistors right here act if they were all one? Take all of this in that circuit and reduce it to him right there. Combine all of those resistors into one, and the circuit should behave the exact same way as long as I add them right. Okay, so that's the idea of equivalent resistance. Now, when resistors are in series, now we're not going to deal with series and parallel combined. That's next lesson. Let's just do simple series, simple parallel. Simple series means all of the resistors are in the exact same line. There are no nodes. There is no way that the current can divide or split up. They're all along the exact same wire without a junction for them to split at, if you will. So whenever you're trying to calculate the total resistance of resistors in series, all you have to do is add them up. 6 plus 6 equals 12 here. 6 plus 6 plus 6 equals 18, so forth and so on. If there were different numbers, 6 plus 4, it would be 10, right? You just add them straight up. Now, in series circuits, two rules you need to remember. The voltage divides up. If this top circuit here, the two 6s, was connected to, let's pick something easy. Let's pick a 3-volt power source. If it was connected to a 3-volt power source across the entire thing, then it would divide according to the resistors, and since they're the exact same, I would have 1.5 volts would drop here and 1.5 volts would drop across the next one. So it splits up. Now, if they were different resistances, then it would split up according to who has the greatest resistance. That's where most of your voltage drop would occur. You'll see that coming up here in the example problems that we're going to do. But since they have equal resistance, equal voltage drop, notice the sum of the two voltage drops adds back up to the total of the power source there. On the other hand, current always remains the same. The current through this, I, let's say 2 amps here, 2 amps equals I, is going to remain the same. It's in the same wire. Current doesn't get decreased in the inside of a wire. It's going to remain constant, and I'll talk a little bit more about that in class. So current remains the same. In series, voltage splits up between all of the resistors. So you start out with 3 volts and it gradually steps back around to 0. So when you start out with 3 volts over here, right, you lose 1.5 here, you lose another 1.5 here, and you're back down around to 0, coming back to the power source where it recharges and continues to go around and around and around. Now, in parallel, things work slightly different. In parallel, the voltage remains the same. So the voltage drop across these parallel resistors does not change, but the current does get to split up, which should make logical sense to you, right? So some current can go here, some current can go here, and some current can choose the top lane. Whenever you're thinking about parallel resistors, I like to compare it to shopping lanes in a grocery store, checkout lanes in a grocery store. The net resistance in a parallel circuit is always less than the resistance of any of its single resistors. Doesn't matter if the resistance is very high or slow. The exact same way that even in a grocery store, if you added in someone with a very high resistance, a lane with a very high resistance, make that a checkout lane where someone comes along and just isn't very fast at doing their job, which is fine, but they're not overly helpful. They don't speed everything up in the store that much. But still, even opening another checkout lane with someone slow still does speed up the net amount of people going through the store a little bit. It does speed up things a little bit. So it always reduces resistance. The more checkout lanes you have open, resistance always goes down. That's why you find this equation. 1 over the total resistance is the addition of all the inverses of the resistances, or of the resistors here. So if you have 3 6-ohm resistors, right, you're going to do 1 over 6 plus 1 over 6 plus 1 over 6, add that up, and then take the inverse of that, and you get 3 6-ohm resistors is just like if you had 1 2-ohm resistor there. Voltage drop, though, I should point out, remains the same. So if this thing is connected to a 3-volt power supply, 3 volts is going to drop across each and every one of these. Okay, so while current divides in parallel, voltage drop remains exactly the same across them. Now I have two circuits here that I want to do examples of, a series and a parallel, and each of them I want to figure out the equivalent resistance. What if all these resistors were reduced down into just one? So this entire circuit was reduced down to a simple circuit, one power source, one resistor there. What would be the resistance of my single resistor? And then secondly, what is the current and voltage drop across each of these individual resistors, R1, R2, R3, after you expand it back out? So after I figure out this, I can then figure out what's happening in each of these individually. So let's start out with equivalent resistance here. In this series circuit that I'm working with up top, you just simply add the resistors. 3 kiloohms plus 10 kiloohms plus 5 kiloohms comes out to be 18 kiloohms. Or if we were converting back to base of just ohms, right, 18,000 ohms. Now, to figure out what's happening in each individual resistor, start with your equivalent circuit. That's the one that's been reduced all the way down to just one resistor with the equivalent resistance now that we know. This is 18,000 ohms. Here. Start there and figure out everything about the circuit. Now in this circuit I already know my power supply, 9 volts, and I have figured out my equivalent resistance. That'll be the first step, reducing from a complex down to a more simple circuit. So now I know my equivalent resistance. The only thing I don't know is the current I inside of it. What is I, the current that goes all the way around, comes all the way around. By the way, I should also point out here, since there's only one resistor, before the resistor you have 9 volts, and then it drops down to 0 volts and then is recharged by the battery, right? Just going to point that out again. Now, how to figure out the current is just using Ohm's law, right, for the equivalent resistance. So V equals IR. V is 9 volts equals a current I that I don't know times R, 18,000 ohms. Whenever I divide both sides by 18,000, I come out with 0.5 milliamps, or 5 times 10 to the negative 4th amps in base units. So now I know what the current is. 5 times 10 to the negative 4th amps equals I inside of my equivalent circuit. Now go back to the rules that we had. In series, current remains the same. It doesn't ever divide up. That means the current coming through this loop, since it never has a chance to divide, I is going to be 5 times 10 to the negative 4th amps. So moving now back to the large expanded circuit, I have enough information to solve for the voltage drop across each one. Check it out. I now know the resistance, because it was given to me, of each of my resistors, R1, 2, and 3. And I came down to the equivalent circuit to solve for the unknown. The unknown was the current that runs through it. The current remains the same through the entire circuit, so because of that rule in series, current remains the same. I know the current in the equivalent circuit is the same as the current in the original series circuit here, which now lets me solve for the voltage drop across each and every one of them. Let me walk you through doing that with the first resistor, and then I'll just go ahead and do the others for us as we go a little bit faster. So the way we solve for the voltage drop across each one of them is going to be V equals IR. Now your first reaction for R1, this first resistor over here, might be, hey, that first resistor has a 9 volt drop. But remember, not all 9 volts drops across that first one. Only part of those 9 volts drops across the first one, and then another part drops across R2, and then the last part drops across R3. But what we can say, because voltage divides in series, what we do know is current remains the same, so we're looking for the voltage V in each resistor. But I do know the current now, 5 times 10 to the negative 4th, and I know the resistance, 3 kiloohms, or 3 times 10 to the 3rd. Kilo means times 10 to the 3rd. So I can tell you that 1.5 volts drops across that resistor right there. Now I'm just going to go ahead and do R2 and R3 for you. Okay, so there you go. All the resistors R1, R2, R3. I found the equivalent resistance. It was 18,000 ohms. And then I used that to solve for the current through the equivalent circuit, working that current back up. Because current remains the same in series, I was able to find the voltage drop using Ohm's law for each individual resistor. I was able to find the voltage drop across each individual resistor. Notice here, voltage divides in series. I have a 9-volt battery. Notice that the addition of all the voltage drop brings me back up to 9 volts. 5 plus 1.5 plus 2.5 brings me back up to 9 volts. So if I'm thinking this through, that means I have 9 volts before I go across the first resistor. Then I'm going to subtract 1.5. I'll have 7.5 volts after I go across the first resistor. Now, after I drop across the second resistor, I lose 5 volts. So now I'm down to 2.5 volts after I get across R2. R3 always takes the rest of it, so it's going to take away 2.5 volts. So now I'm left with 0 volts, going back around to the battery where it recharges and continues the circuit. A note here. You are always left with 0 volts after the circuit is all the way done. You always start out with whatever's in the battery, and then all the way around the loop you'll be left with no voltage left after it's gone through all the resistors. All right, so now let's do the parallel circuit. Now remember, in parallel, voltage remains the same and current divides up, meaning that across each of these 2 ohm, 3 ohm, 4 ohm, each of these resistors, I'm going to have a voltage drop of 1.5 volts. Notice that the battery is in parallel. Notice the parallel lines, right? The battery is in parallel with each of these resistors. Notice the current can divide. Choose which line it wants to go down. So the current can come all the way down here. Let's actually draw that out. The current could come all the way down here. The current could go through here, or the current could go through here. All right, so it has a choice to divide between them all. Now, to find equivalent resistance, that's another term for total resistance, right? And so I purposely wrote this equation over here using equivalent resistance to get you used to that. To find equivalent resistance in parallel, I use the inverse. So 1 over Req, or RT, equals 1 over all my resistances. So 1 over 2 plus 1 over 3 plus 1 over 4. Whenever I punch the right-hand side of the equation into the calculator, I come out with 1.0833, and unfortunately, that's where most people seem to stop. That's the number one mistake I find students make when adding resistors and parallels. They get to this point and they stop, but they forget they have to solve for Req, and you have over here 1 over Req, meaning that you need to take the inverse of each side. The equivalent resistance, or the total resistance here, is going to be 1 over 1.0833. That gives me an equivalent resistance of 0.923 ohms. Please forgive me for not using proper sig figs in the pictures that I have going in the previous problem. In this one, there was only one significant figure in the variables or in the resistors, so I'd have to round. So keep that in mind whenever you're doing actual problems here. Now that I know the equivalent resistance, I can solve for each individual idea of voltage and current through these 3 resistors here. And actually in parallel, I wouldn't have to get down to my equivalent circuit right here to solve for that, but I'm going to go about it as if I did. The one thing I don't know now is the current inside of this circuit. I equals question mark, because I do know this equivalent resistance now. Total resistance, not 0.923 ohms. So to solve here, I just need to use Ohm's law. V equals IR, and solve for I. And I come out with the total current through this circuit should be 1.63 amps. Now looking at the original circuit, this is parallel, meaning that the current divides. So all of these currents flowing through these lines should add back up to be 1.63 amps. It's like I have 1.63 amps flowing here, and then it's going to divide out like this. I'll call this I1 through my first resistor, I2 what goes through my second resistor, and I3 what goes through my third resistor. And whenever they combine, again, I1, I2, and I3 combine all the way back up into this last lane right here, I'm back up to my 1.63 amps. So it's going to split up and then recombine. Current divides in parallel, but voltage remains the same. That means the voltage drop across each one of these is 1.5 volts. because notice it's in parallel with the battery as well. So each one of these has a 1.5 volt potential difference drop across from it. So I can use V equals IR on each one of these. So the current through the 2 ohm resistor is 0.75 amps. Notice that I used 1.5 volts as the voltage across, the voltage drop across this 2 ohm resistor, because once again parallel voltage remains the same, 1.5 volt drop across. This is why I don't necessarily need the total current, but what we're going to find out is that all the currents added up, so this is the current through the 2 ohm, current through the 3 ohm, current through the 4 ohm. Whenever you add them all up, we're going to get back to our 1.63 amps. All right, so now I've calculated my equivalent resistance over here. All the resistors added up using the inverse rule, right, for parallel, 0.923 ohms. I had to round that a little bit there. I know the voltage drop across each one of these individually. Whenever I break it back out, it's 1.5 volts because these are in parallel. Voltage remains the same in parallel, so 1.5 for each of them. So it starts at 1.5 drops across down to 0 across each of them. Shopping lane style, right, in the grocery store, checkout lane style in the grocery store. Using the fact that each resistor has a 1.5 voltage drop across it and its resistance, I was able to calculate the current that goes through each of them there. So now I know the voltage drop and the current across each resistor. Notice that as the resistor gets larger, the current goes down, which if you're thinking back to the metaphor of shopping lanes, right, of checkout lanes in a grocery store, the slower or the greater the resistance in a shopping lane or a checkout lane, the slower the people get through, the lower the current. All right, try to digest all of this stuff. Make sure that you write down any questions that you have and bring them to class tomorrow, and we will talk about it and try to digest it a little bit more in class together.